PowerPoint is a little bit big, but let me say 8 gig or 8 meg. So
yeah, that's fine. I can take that.
okay. See if you got this new one that I sent. So it's Sri presentation version 3, F3.
Okay, everyone, it's 1 o'clock, and I appreciate you joining us for this MATS UTC webinar today. I think we're going to give us another minute to get organized, and then I'll start with our beginning part here. Excuse me. Okay, welcome to our MATS UTC research webinar series. Today we're going to talk about the impact of climate change and sea level on stormwater management in Hampton Roads. So I did want to, before we start, I wanted to show us our list of webinars this spring. This is our 4th of 5 webinars. You can see what the other ones are. I'm hoping that you will join us in June for our LIDAR for Air Quality Measurement webinar, presented by people at mostly Old Dominion, and then they have a partner in Virginia Tech. So if you want the recordings for any of these webinars, I have the link up here at the top of this slide, but you can also just go to matsutc.org. You can search for webinars, and then you would get the list for webinars, I think is their first thing. And then you can see all of our MATS UTC webinars. You can definitely get the links for all these. You can get the presentations for our past webinars in PDF. So I'm hoping that you can learn from these. You can see the archived recordings also. So with that, I want to, before we do all that, I want to ask you a few questions if you've attended other MATS UTC webinars recently. I've been asking the same few questions. So whether, we do have somebody who says that this is the first webinar they attended and then they changed their answer, okay? So, people that are responding here, I do have 3 questions before we start with our first presentation. So I guess, yeah, most of you guys have been to other MATS UTC webinars. Welcome. And we have at least one person who's attending his first one, so that's awesome. I also wanted to ask, I'll go ahead and end this. I wanted to ask if you work at a MATS UTC university. And so I'm getting actually lots of different answers. We definitely welcome your public agency folks. I'm hoping that you and others find this useful. Great. And then, all right, so with that, I'm going to go ahead and move that over. So welcome to everybody. But I also wanted to know whether you know at least one of our today's presenters, and if that's like why you're joining, so that sort of for my curiosity. So the answer is yes and no. So which is good. So fantastic, and thank you for our additional folks joining us. I'm going to go ahead and load we have a few slides of you here that I think Professor John Goodall of UVA is going to start our presentation, and I screwed up and didn't start this at the front. I'm sorry. Here we go.
Okay.
There we go. So I'm going to let John Goodall present today. We are going to be joined by Venkat Sridhar from Virginia Tech, and so John's going to tell us about their project. Go ahead,
Okay.
John.
Can everyone hear me okay?
Stormwater, yeah, I can hear you.
Great.
Do you want to talk about the stormwater management question now or later?
Maybe we could do it right at the end of this slide set. Would be good.
That's
So, so thanks everyone for joining. My name is John Goodall, and Sri, do you want to say hi real quick so they hear your voice?
Hello all. This is Sri from Virginia Tech.
So we got a MATS UTC project that we've been working on over the last year or so, and we're going to present some of the results from that work today. And this is the title from the project that we got funded, Impact of Climate Change and Sea Level Rise on Stormwater Design and Recurring Flooding Problems in Hampton Roads. And really what we proposed were two objectives. So first, before I go to the objectives, here's a little bit more, since at least half of you don't know us according to the polls. Here's a little bit of an introduction. So Sri's an assistant professor at Virginia Tech, and he's actually in the Department of Biological Systems Engineering. And he's an expert in hydrology, water resources. He's done a lot of climate downscaling through this work. You can read his other background and different. We're both professional engineers, which is it's a good thing. And here I am. So I'm an associate professor in civil and environmental engineering at UVA, and my background's really in hydrology, GIS, hydroinformatics, and doing some work, good bit of work these days from the Virginia Transportation Research Council. So it's looking at stormwater impacts on transportation, flooding impacts, these types of things. So at least you could see our face at least from those pictures, since it's over a webinar. So we had two objectives with this project, and these were basically broken down in terms of what Sri focused on and then what I focused on. So this first objective of quantifying rainfall intensities, distributions, frequencies using climate models and trying to downscale those to a scale that they might be helping with transportation design projects. So if you were to build a project today, we know with climate change that the future rainfall intensities, distributions, and frequencies will be different, but we don't know exactly how. And so the research question is, can we look at some of these climate models, downscale them, and get some kind of measure of what, looking in the future, what a 100-year storm might be, for example. So Sri will present some research outcomes from that. And then my focus was more on trying to understand this reoccurring flooding problem, and mainly from tidal-induced flooding, but also kind of a storm surge type of approach. What roadways within? We focused in particular on Virginia Beach and Norfolk for this, rather than the entire Hampton Roads district, because we were using very high-resolution LiDAR data, but we were able to identify roadways that are low-lying and might be vulnerable to flooding. So I'll present some of the research from that. So I think that's it for the intro slide. So I think one of the things we wanted to do beforehand was get you to answer at least one question so we can kind of gauge what the audience knows about stormwater management. So if you don't mind, while the slide set flips over to Sri's presentation. And I think that, at least for me, that poll went away when you switched the slides. Emily. So Emily, if you're talking, I think you're muted. I'm not sure.
Sorry, I did
No
mute
problem.
myself. Thank you. So here I will try to make the poll come back as I upload here, and I am not succeeding, so I have screwed that up. And so I'm sorry, but hopefully it's going to be worth it to get this the presentation correct. And what we wanted to ask, here it is. Here, do you work in stormwater management? Just to give us an idea of your familiarity with the topic. So hopefully everybody can see this now. Sorry for my fat fingering there. And the first people to respond say they're here to learn, so I think that's a good sign. So thank you for responding to this.
Thank you.
I think we do have the presentation, sorry, moving it, converting. So it's coming. And then we will let Sri present in a minute here. But I think this is good, so you guys understand that we don't know a lot about stormwater here. And maybe we should have asked a similar question on how much do we already know about climate science? And maybe we can assume maybe not lots. So with that, Sri, I'm going to move the poll away, and then you can go ahead and start.
Sure. Thank you, Emily.
Yep.
All right. So good afternoon to all of you. So again, thank you, John and Emily, for organizing this. And the topic again, as John introduced, impact of climate change and sea level rise on stormwater design and recurring flooding problems in the Hampton Roads region. So the first part is about climate change, and I have my co-authors Prashant, Valaya Kunnath, and Mirza Billa, the postdoc, to acknowledge their hard work on this project. They have come up with the analysis that I'm going to actually show in the next few minutes. So just to give you a primer on climate change, I'm sure most of you are aware of this standard graphs, but I just wanted to introduce again the same concept of climate change from past to future, how things are changing with respect to emission levels from SRES or SRES A1 or A2, B1 scenarios that you are seeing on the left side of the panel, and the new jargon that we are using in the climate modeling field is RCPs, or representative concentration pathways. 2.6 and 8.5 are the lower end and higher end of emission scenarios, equivalent emission scenarios, but it's mostly determined based on the radiative forcings. And 8.5 you can relate to A2 on the left side, and 2.6 you can relate close to conservative B1 scenario of the CMIP3 generation of climate modeling. So what you're seeing here is increasing temperature, and for the past 100 years or 50 years, 1900 to 2000 or so, and then from 2000 to all the way up to 2100, you can see a sharp increase with RCP 8.5 and a very modest increase or even plateauing with RCP 2.6. So when we talk about climate scenarios, of course, anything in between these scenarios can happen. So there are multiple models that I'm going to actually talk about briefly and see how we have taken these outputs from these models and processed for hydrological applications. And what you're seeing here is projected change in average temperature on a global scale. Of course, 2.6 has got a modest temperature increase of 1 to 3 Fahrenheit, whereas RCP 8.5 shows a dramatic increase of even up to 9, 10, 11 degree Fahrenheit increase. And that's pretty dramatic, and it probably has a lot of ramifications on hydrologic cycle and how we manage our systems here. So projected change in average precipitation, what we are seeing here from 2.6, it's modest change on the left side of the panel that you see, except equatorial regions, including sub-Saharan Africa regions and also the Middle East. In the North American region, you don't see too much of a change, but on the right side, you can see a substantial change with respect to increased precipitation all over, Eastern Africa to Asia, and then part of the changes that we are seeing here is not so clear, but on the eastern part, we are looking at northeastern side increased precipitation. So I'm going to actually show you some numbers to back up that argument. So what we are seeing here is, I'm sorry, I think I may have to make it like a big screen here. So so with the increased temperature, they want to see what's happening at the local scale. That's the drive that climate modeling communities going after for understanding what all these climate models mean when it comes to understanding what will happen in my backyard. So when we talk about the regions here, they have divided into multiple regions for the entire country. So we come under southeastern region. Of course, we are talking about increased temperature, and then of course there was some decline, and then of course you see in the late 2000s and beyond increased temperature that we are seeing for our region. But on an average, all of the regions are showing increased temperature. And then for the precipitation part, of course, it's not so uniform like temperature. Variations in precipitation is quite obvious. Some regions are having decreased precipitation, some regions are having increased precipitations like the upper Midwestern region. For Virginia particularly, if you focus on this region here, we are talking about increased precipitation. Northeast, although it's quite obvious, but in our case, of course, the Shenandoah Valley and probably in the northern part of the state and also eastern part, which is of our interest for this particular project, we are seeing increased temperature of up to 7-10% increase. 7 to 10% increase in our precipitation changes in the past, but again that's seeing that's actually translated into even heavy amount of precipitation that we are seeing from the observed data sets. So for this region, that what I'm showing here as 27% northeastern region, of course this is taken from NOAA report, so they are estimating 27% of increase based on just the observed record of rainfall. And relating that to also sea level rise here, historically, of course, there is a gradual change. They have used different data sets, proxy records to tide gauge data, and then satellite data. So in the future, the most important part that we want to be highlighting here is, of course, 1 to 4 feet of increase in sea level rise, and that's pretty much in our backyard, in Virginia Beach and all the eastern regions that we are interested in looking at what kind of impact that we will have because of that. And again, historic changes that we are seeing about 1.7 millimeter per year of change with respect to sea level rise or sea level change. And then here in the last 20 plus years or so, we are seeing a dramatic increase of 3.32 millimeters per year again. So this is all from the observed records of some locations along the Virginia Beach region here. So again, in the southeastern region, this translates to some of the specific questions. Sea level rise, that's going to pose significant widespread problems in terms of resources, economy, and environment. Extreme heat will affect health, energy, agriculture, and more. Decreased water availability is also on the forecast or projections. Infrastructure is being damaged by sea level rise, heavy downpours, and extreme heat. It's also going to change significantly because of climate change. Just briefly talking about temperature change, of course, we are seeing more number of 90-degree days. And then, of course, historic to projections, if you see the same, days that are below 32 will be decreasing, and then days above 95 or so in the summertime is going to be increasing. And that's all having an effect on the hydrologic cycle. And of course, that's related to precipitation, and precipitation change will be impacting how the stormwater management systems are handled. Again, the guiding question here is what structural and economic issues arise as a result of rising sea levels? How do coastal communities respond to these issues? And then identifying the factors that put certain communities at risk. And then how can rising sea level affect agriculture? This is kind of an overarching question that scientific community is going after for many regions, and that is very specific to this region as well. And vulnerability of sea level rise. I'm sorry for the type or the display of some of these titles here. Vulnerability, as we see here, of course, the entire East Coast region is kind of affected. Of course, widely reported projection problems are for New Orleans, which is kind of the #1 target when it comes to sea level rise and subsidence. But then Virginia Beach is not too far from New Orleans in terms of the risk factors. And they are rating now Virginia Beach as #2 in the nation in terms of the risk of sea level rise and impacting on the infrastructure. So again, that's going to have an effect on transportation. Sorry for just quickly going over this, but just I wanted to give it as a primer to see how these different sectors are affected. Mean sea level rise in different cities are being studied, and of course for Norfolk region, if you see here, I may have shown in some of my previous presentations. In the interest of time, I'm just giving the link here where they talk about how sea level rise is impacting the communities in this region. And of course, that factor of risk is incorporated in many of these design principles or practices that we would like to be doing. And for this particular project, coming briefly with all this climate change introduction to this region, we are actually looking at multiple pixels in this area of southeastern Virginia. Mainly these red points that I'm showing here are global hydrologic network of precipitation records that we have, and we wanted to actually use these data sets to compare against climate models, to vet them, to validate how good are these models, and see whether or not we can trust them. That's the primary goal. And historic data first, of course, is to be analyzed, daily and hourly precipitation, and then we also try to bring in this CMIP-5 multivariate adaptive constructed analogs. This is again developed by University of Idaho, and they have done it on a countrywide scale, but then we are actually trying to really zoom in on our region and try to downscale it further using WRF model. WRF is another meteorological model, weather research and forecasting model for 1985 through 2010. We just wanted to see how good are these climate models. When I'm talking about climate models, these are the list of models that we looked into. These are developed by different research labs and centers around the world. And the resolution that we want to be looking at is at 1/16th degree, which translates to about 4 kilometers or so. These 15 GCMs on a daily time step for 150 years or so, that records that we have, we wanted to actually look at them at this high resolution of 4 to 6 kilometers. And then we also validate or downscale them using these WRF models, downscale to hourly data set. Notice here that we are talking about climate models at the daily time step, but then we want to be essentially converting them for intensity, duration, frequency analysis at the hourly time step. And what we have done is, of course, WRF model is really a monster. It takes a lot of time and resource computationally to run this at a high resolution, like 1 kilometer or less for the entire region. So we wanted to kind of test the scenario first with 1985 to 2010 and see whether or not we can trust these climate models and how much of an agreement that we see between WRF and CMIP-5 data sets. And again, this is done at the same resolution here just to understand whether these current generation of climate models agree with weather forecasting models. What we are seeing here is observations in blue line, and MACA, or the climate model median records that we have is in dotted lines, and then MACA average that we have in gray shaded area, and then WRF from this weather research and forecasting model output using NAR data set is in red line. So again, this is just to see whether or not we capture the trend. So in essence, of course, there is a big variability that we have. Annual extreme precipitation data measured by this USGS CND data set, actually Global Historical Climatology Network data set, of course. For the most part, they agree. In essence, they come in within the range of these climate model predicted projected precipitation changes. In the past, of course, this is again, notice here, this is for the past conditions. We wanted to validate the model, and then we generate these hourly precipitation data for the short period of 1985 to 2010, and then we check if they are coming close, but in some places they agree, in some places they don't agree. So that is the message from this particular slide, but then we wanted to really understand what kind of bias we have from all these models when we compare that with climate models, and see anywhere between about 13 to 25% increase or change with respect to precipitation predictions are possible. Again, this is annual extreme precipitations that we are looking at just for IDF curve generations, and of course, some models are close to observation. Some models are too far away. So these are the things that one needs to take into account when it comes to considering them for design purposes. WRF model has a bias of about 20%, and again, that's also primarily due to the parameters that we have within the model for both atmospheric modules and also for the land surface part. For this particular exercise, we did not calibrate any of these models. We just tried to run them and then downscale them at 4 to 6 kilometers, and then get the output to compare. And what we are looking at here is the historic precipitation gridded data that we got from these climate models, and these red dotted lines that we have are from the observed locations or the gauge data set. And then, of course, you see here on the middle panel 4.5 for 85 years or so, and then RCP 8.5, the extreme scenario on the right side of the panel here. Anywhere, I mean, if you look at, for example, Hampton or Norfolk region, of course, you are seeing some level of increased precipitation. If it's about 200 to 250 millimeters precipitation on a given time period here, we are talking about this for the same corresponding period. It's 300 millimeters of rainfall to more than 700 millimeters of rainfall. This is again the monthly averages that we are showing here. That same number, of course, can change depending on the models that we use. Observed with least extreme precipitation distributions that we have here is coming from this RCP 4.5 compared to historical, and then of course RCP 8.5 is showing really increased precipitation for most of these regions along the East Coast. And again, extreme precipitation for 15 from these climate models when compared with observations along side by side. We are looking at a reasonable increase of up to 500 millimeters, even sometimes more than 700 millimeters of rainfall for extreme precipitation of the highest annual amount of precipitation that we get. And of course, that number doesn't make much sense as we see in a gridded product, so we wanted to translate them directly in terms of IDF curves. What we are looking at here is the flood frequency for 24 hours. On the x-axis, of course, you see the return periods. On y-axis, you have precipitation for 9 of these locations. And the red one, again, I'm sorry here for changing the color here, but the red one is the observation and RCP historical, and from GFM model, and then the other one is BCM model that we are showing here. There is a difference. Majority of the sites, of course, you can see the black line is a little bit above the red line. So what it means is, of course, the intensity is changing. And closely looking at this graph, if you see here, this is the 100-year. For example, Norfolk Airport, I'm talking about here, you have, let's say, 150 millimeters of rainfall in the past, and that's going to actually change to 175 or so. And that can happen in the 100 years time. Or if I relate this 100-year precipitation to the same depth of precipitation, it can happen even in 50 years time. So that's the message that I'm actually getting at overall when it comes to increased precipitation and when it happens and what kind of time interval that we are talking about. So this is from 24 to 48 hours that we have shifted the analysis. And of course, again, it's a summation. It's more of a statistical exercise than understanding what's happening with respect to the physics of the atmosphere for 24 to 48 hour time difference. What we are looking at again is a dramatic increase in precipitation. Return periods particularly are decreasing for higher amounts of rainfall, and again that is pretty much what we are showing here is for selected models, and that's true for other models as well. And for historic times, of course, if you look at flood frequency for 24 hours, 1950 through 2005, the intensity is, of course, is shown in the red line here, but then the gray shaded area is about all these model scenarios that I talked about for historic times. And you have these models like I talked about before. There is a range, right? These projections are not just sticking to one particular historic trend. We are talking about some decreased tendencies, and in some cases there is an increased tendency, and the observations fits right in the middle. And that's true for the most part, and some exceptions are there. And for 24 hours into the future, if you see for the next 85 years, there is a range. We are looking at the range in terms of precipitation depths for multiple locations that I'm showing here is widely varying, but still, if you take the average or if you take even the extreme scenarios for planning considerations, that gives us the idea that, of course, precipitation as high as 70 or 700 millimeters or as low as 200 millimeters for one particular location is possible. So that is the take-home message from this particular analysis. Again, we look at RCP 8.5 for 24 hours. What we are seeing again is aggressive scenarios of increased precipitation for sure in many locations, although the uncertainty is also widely varying and increasing, and that's the trade-off that we have here with respect to higher-end emission scenarios where the uncertainty is also more, but you get to see what level of increased precipitation that we can have from all these models. Again, this is flood frequency for historic times. I don't know if I need to show this, but I should have shown this before. But in essence, there is a change with respect to historic to future here for 48 hours of RCP. Essentially, we are talking about increased precipitation, same as what we have seen in the 24-hour analysis, 24-hour records. Also, for RCP 4.5 to 8.5, like I can go back again, you can see the gray shaded area for certain locations or more when we compare RCP 4.5 with RCP 8.5. So what I'm referring to here is this kind of gray shaded or green shaded area that we have is increased number of depth of precipitation that we have. So in conclusion of this particular analysis is that we have this level 1 data with bias, meaning we have shown some of these outputs just as downscale products which are bias corrected at the first step when we talked about climate model data set downscale to MACA scale of 1/16th degree, and that's about it. We did not change or we did not do the bias correction within this precipitation data set with observations. Again, that's the level 1 product that we have, and we have compared that with WRF models, and we try to actually see the bias. So like I mentioned before, we are talking about bias of anywhere between 20 or 15 to 20% of precipitation change when we compare with historic observations and also within the models that we are seeing. And bias corrected process data is of course essential, and the ways of doing it of course is going to change depending on the data set that's available for us. And of course the initial assumptions, what we are doing here is basically to take out that bias that what we have in the projected precipitation just on a monthly time step, and then apply downscale them to a daily time step and see if the 24-hour 48-hour increase to precipitation comes close to any of these observations, and also with this WRF model downscale products. So gridded product of precipitation shows general increase in precipitation anywhere from 700 to 2100 millimeters of from the annual scale, and then of course for the most of these GCM products, decreased return periods and increased intensities might be likely over the study region. Of course, I have the gridded product for all of these locations that has the time series for each of these pixels from all the way from 1950 to 2100, and impacts on the local scale, hydrology and hydraulics is going to be there, and of course we are looking at that and see how this increased precipitation changes into discharges. And of course we are closely working with John on this. We try to actually translate this precipitation into runoff and see how revisions to our design approaches or even to the sizing of culverts to all the other design features that we have for stormwater management should be considered. So that's where I want to actually lead this discussion to the next step. So essentially we are just getting these precipitation products out to link with hydrological applications in the next phase. So John, would I pass this to you to the next presentation?
Actually, I'm going to break in here. Do we want to ask about how much they're using climate change science right now?
Sure. Thank you, Emily, for reminding. Yes, that would be wonderful. if you can answer, how much are you using in terms of climate change science for your decisions or designs, current designs, and then decision making? If you can answer that.
Yeah, if your answer is none or somewhat, I think we're interested in, like a why. If you're willing to type that in, I think we all can see the answers then after you hit enter. So then I did want to apologize for some of the titles in Sri's slides. Got the system, was unhappy with them, but you should be able to see get the PDF on the left here. You can get the PDF of Sri's presentation, the PDF of John Goodall's presentation, and also just the few slides of overview, if that's helpful to you. So it looks like we have, the 8 of so half of our people have voted here about whether they're using climate change science. Nobody is coming up with a none answer. So I can go ahead and, we got a couple more votes coming in. Where I think we'd love to hear from, or the presenters would like to hear from the significantly people, so that, definitely feel free to chat in the chat box. If people have, questions for Sri as we are trying to switch the presentations here, I think Sri can answer a question or two. Then we do want to have John Goodall present, and then go ahead and have questions at the end in general. But yeah, if things occur to you as people are talking, please use this chat box in the lower left here. Please, again, if you download the presentations, I think you'll have, they're slightly clearer. So I am going to go ahead and move the polls. Thank you for your votes. And go ahead and stop this one and try to load the next one, which shouldn't take as long, but it is this one. A little bit, it's a bigger file. And then as that one's coming up, we had one more fill-in-the-blank question of, if you were to consider climate change in your work, what are your data needs? Because that's something that both of our presenters are interested in. Yeah, we didn't have success with people filling in before. I'm going to go ahead and move this one. If you have data needs, we do have somebody typing in the left here. Maybe filling it in the box on the left is a way to share us with it. So I do have, interesting. So Andrew Scott has written in how the I-64 high-rise bridge project will include 5 feet of additional height to provide clearance for vessels. So, but I'm happy to hear that VDOT is paying attention to these things. So here's the need: spatial and temporal sea level rise projections for the region. So you guys, I think we get the concept that there are needs. I appreciate that we are getting more people joining us. This might be the largest number to attend one of our research series this spring. So thank you. And again, the archive and the presentations are going to be available on our website for all. So I am going to, how much and how fast? We got an answer. So I'm going to go ahead and move this. Definitely if you want to add more responses, please put them in the chat box. And I'm going to ask, this is the correct presentation. I'll ask John to do his presentation.
Okay.
Thank you.
All right. Hi, everyone. Can you hear me? Hopefully you can hear me. Yes? Okay.
If you could speak a little bit louder, that'd be great.
Sure, I will do that. All right, so I'm going to talk about some of the research we've been doing related to this project, and I want to acknowledge co-authors here. Jeff Sadler is a PhD student here at UVA. Nicole, Kim, Allison, Veronica, and Jordan are actually all undergrads. They actually just graduated, and they worked on this a little bit too as part of a senior capstone and an independent study class with me this past year. So they all contributed to this presentation. Okay, I think this kind of goes without saying here, but just in case, sea level rise. I think this is one of the major problems facing coastal cities throughout the world, and I think Hampton Roads is nationally known, if not internationally known, as one of the case studies for this. And I'm sure you guys already know that. But when I go around and talk to, I was just last week at a conference down in Florida, and there was a lot of talk about this in Hampton Roads is near the top of people's lists of places that are going to be impacted. It's really hard from a hydrology perspective to understand and get water off the landscape. So if you don't do stormwater work, you should just know it's a very challenging environment because there's most of the stormwater systems are driven by gravity and there's very little topographic relief. So it's hard to get the water off the surface. And so these coastal cities in Virginia Beach, I know, and I think maybe Norfolk as well, are turning to pumps to try to move water around for that reason. What you don't hear as much about, but I think you should hear more about, is these tidally influenced flooding events. So we do hear a lot about storm surge and these mega storms that come through and cause lots of flooding. But these tidally driven floods that are happening now, I know in Norfolk and Miami Beach and other coastal cities are also very disruptive and are going to be increasingly disruptive as sea levels continue to rise. So on the right there, you'll see these are some sea level projections, sea level rise projections. I'm going to talk about this a little bit more on a later slide, but this is something that's been produced by the Virginia Institute of Marine Science and that we're using in our study. And this is Houston that, of course, is another one of the cities that is highlighted pretty often in terms of flooding. This is some of the floods they had, picture from some of the floods they had not too long ago. So really we want, in this sub-project of the overall project, we had two research objectives. Can we identify segments of the transportation network, looking mainly here at VDOT roads within Norfolk and Virginia that are vulnerable to flooding caused by, and we're looking at these three different factors here. We're looking at tidal fluctuations, so during a high tide event. We're looking at sea level rise, this kind of long-term sea level rise projection that's happening. And then we have just kind of an estimate of what a 100-year storm surge would be by looking at tidal gauges and putting that as a third factor. So looking at those three factors, can we say what segments of the transportation network are vulnerable? And then we also overlaid some traffic data from VDOT. So the question isn't, so some roads might be vulnerable, but they might not be heavily traveled. So we're actually looking for roads that are heavily traveled and vulnerable as being highest priority places to look at. So one thing to say that we didn't really focus on here is when we initially set out to do this, we were thinking also about precipitation-driven flooding. But as Sri showed through his presentation, it's really hard to get a good measure on precipitation and precipitation patterns in the future. I think we're getting closer to that with some of Sri's work, but there's still a lot of uncertainty about future precipitation patterns. So we're really just looking at these factors of high tide, sea level rise, and storm surge, and not really layering on precipitation quite yet in this analysis. So quick summary of the methodology. So we went and collected the transportation data from VDOT. It shows the road center lines. We have a very high resolution LiDAR data set, about 2.5 foot resolution LiDAR data set that we use for this analysis. That's publicly available if anyone's interested in getting a handle on that. It's a very large data set, so it's difficult to work with. You have to be very patient with it. And then we went and tried to, from tidal gauges, try to figure out what the tide fluctuation might be, storm surge, how your storm surge might be, and what sea level rise might be in the future. And then we used GIS analysis and ArcGIS to try to put all that information together to identify these roadways that are vulnerable. And then again, by using the traffic data, we try to identify which are the most heavily traveled roadways in Norfolk and Virginia Beach that are vulnerable to flooding. So here's a picture of the roadways, the VDOT roadways within Norfolk and Virginia Beach, and they're basically being colored by their elevation. And these elevations are, again, on a 2.5 foot interval, or resolution, if you will, and this is derived from the LiDAR data set. So this is the real kind of, we did a lot of processing to try to create this data set where we would know along the roadways how high they are in terms of elevation, and then this is one of the main data sets we use to see which ones are going to be vulnerable from different sea level rise and high tide scenarios. And we're happy to share any of this data with anyone who's interested. Just say that up front as well. This is a picture of this average annual weekday traffic, daily traffic that we also obtained from VDOT, and we have that for each of the road segments within the data set. We have this number as well for identifying which of the roads are most heavily traveled. For getting the storm surge and the tide data, this is our approach. we used a tidal gauge, this Seawell's point station, and it has information, historical information basically about this 100-year storm event. So we took this to be like a storm surge scenario, and I have a table coming up with these numbers. I know you can't see them really well here, but I have a table summarizing these numbers in a second. But the 100-year storm surge, water surface elevation, the mean high tide elevation, and then you have to take care of all the datums and these types of things. So an adjustment into this particular datum that we're using so that all the numbers are in the same datum. And this data is publicly available online, and if you want to try to find it and you aren't able to find it via Google, let us know. We can point you to it. So if you take all that data and you kind of put it together, this is what you would get. So from year all the way back to 2000, all the way up to 2100, and there's these different scenarios for sea level rise, as you could see in that prior slide. So let me go back one slide here. So we have like a high emission scenario, like worst case scenario, a low scenario, and an intermediate scenario for sea level rise, and we're carrying that through the analysis, those three different levels. And so here, for example, if you look at just the intermediate sea level rise plus tide, like plus a high tide, these would be the elevation of the water surface in meters, and this range column here is capturing that uncertainty from the sea level rise. So for all the way from the low to the high scenario. And then these numbers here are now sea level rise plus tide plus this storm surge, this 100-year storm surge. What would the water surface be? All right, so we try to just kind of very simply calculate what we think the water surface would be, and to use that along with that transportation elevation data set I showed on a prior slide to say, okay, which roadways do we think would be inundated? And this is a simple approach, fully aware of that. Storm surge is very difficult to model, and there can be very sophisticated ways using hydrodynamic models to try to simulate storm surge and exactly how it would work. But I think this is a good kind of back of the envelope way of trying to assess vulnerability. So I'm sorry these slides didn't come through quite as nicely as I wanted them to, but all this is really saying is we calculated the flood water elevation for a given year in scenario 1, where we're looking at just tidal-driven flooding or recurrent flooding. That is just simply the sea level rise for that year plus the mean high tide. So we're assuming the mean high tide is going to be constant over the next 100 years. Again, we know that that's not maybe the best assumption, but it's a good back of the envelope assumption. And then we did this datum adjustment as well. And then scenario 2, we basically did that same thing, but then we added on also this 100-year storm surge. So this is scenario 1, kind of more of this recurrent flooding one, and this scenario 2 is more of a a mega storm or large storm, 100-year storm flooding scenario. All right, so if you take all that information together and just kind of summarize it briefly, this is one way that we've done that. And what we did here is just over the whole domain, what are the percentage of the roadways that would be inundated or flooded. And so starting off at year 2000 all the way up to 2100, and then the two lines there you see, the lower line, that lighter blue line, is just this high tide plus sea level rise. And then the darker blue line is, again, putting storm surge on top of that. So, and the error bars here are really coming into play from the sea level rise uncertainty. So you can see, I think just roughly, even right now, these large storms, obviously we think they would impact about 25% of the area. And in the future, it could go up all the way to 70% of the area would be flooded from a 100-year storm of the roadway infrastructure. And if just from the tidal influence, 2100, we're thinking it's potential about 10% of the roadways here would actually be inundated at high tide. From a kind of a rough approximation. Okay. So we took it. Now this. individual area uh, uh, when you layer on this traffic information, that uh, uh, might be vulnerable to flooding. And so again, I can share these slides, or I guess you could just download these if you want to see a little bit cleaner of a version and kind of zoom in and stuff. But we've identified locations here that um, have a low elevation. So a low elevation along with either like medium traffic or high traffic. So the red segment here are the you know $75,000 or more or um, uh, uh, average annual weekday daily traffic. Uh, think that those would be the most critical places